What's up, everyone? Welcome to the MK Labs. Glad you're here. This is the first video on the MK Labs and the start of the series I've been wanting to make for a long time, called AI Native Quality Engineering. It's about what happens to testing when the thing you're testing isn't deterministic anymore. Across these videos, we will cover the architecture of production AI systems, what evaluation really means when there is no clean oracle, the anti-patterns I see in almost every AI testing engagement, and the parts nobody talks about, the drift, self-heal, evaluation pipelines that don't lie. This first video is the landscape, a real story, a real architecture, and 4 reasons testing AI gets harder than you would expect. If you ship AI in production and you're about to, this is your terrain. Let's jump straight in. So I built an AI test generator, not a prototype, not a weekend experiment, a real system, one that crawled production interfaces, wrote assertions, and ran them in CI. And it worked. At least that's what I thought. Because here's the thing about AI in production. You're not just shipping a model, you're shipping a decision-making system. And my test generator was making decisions about what to assert, how to verify outcomes, and what correct meant, all on its own. The problem wasn't getting it to generate tests. It generated plenty. The problem was that I couldn't trust them. This talk is the story of what broke, and more importantly, why it broke. Because the moment you introduce probabilistic components into your testing pipeline, your entire test playbook, the one that you've relied on for years, starts to quietly fall apart. Your test can be green and you can still be broken. That's the terrain we are in. And that's what we are going to unpack today with a real story of what I built, the architecture behind it, and the lessons that changed how I think about production AI testing. 100% pass rate and 21 days of broken refunds. Because this is the kind of failure that make leaders lose trust in entire delivery pipeline. The test was passing, the feature was broken. And both of those statements were true at the same time. Now most teams hear that and assume flaky test or bad environment, but that's not what this is. This is worse. This is a test that looks valid, runs reliability, and still asserts the wrong thing. This is the gap. The gap between what your test suite claims and what the business is experiencing. The pass rate was real, the bug was real, both true at the same time, and here's what I want you to notice. The AI didn't fail in the way people imagine AI fails. It didn't hallucinate nonsense. It didn't crash. It didn't throw any error. It did exactly what it was asked to do. The problem is, we asked it to do was harder than we realized. We asked, write a test proves a refund worked. And the system answered, here is a visible confirmation on the screen. That sounds reasonable. It's just not a ground truth oracle. So when people say AI testing, I want you to think you're not just testing software anymore. You're testing the meaning of correctness. If you ship AI in production, this is the terrain. Who this is for? QE leaders, ML engineers, architects, people who own AI in prod and are getting nervous. Because you can feel it, the old rules don't apply cleanly anymore. Test pyramids, stable assertions, deterministic execution. They were built for a different world. What you will leave with today is 3 things. First, a real architecture of how production AI systems are actually built. Second, 4 categories why testing gets hard. And third, what I think replaces the pyramid, not as a slogan, but as a practical structure. The aim here is clarity, not hype. Not AI will solve everything, just a reality of what happens when probability enters the delivery pipeline. Here's a failure in one diagram. The crawler plus DOM analyzer scanned the page after the refund action. It looked for the most prominent post-action element, and it found the toast, the refund processed. So the generated test asserted toast.equals refund processed, green run for weeks, but meanwhile in the backend, the transaction state was never changed. It stayed pending. This is the key. The UI signal was not coupled to business state. The toast fired whether the refund actually completed or not. So this is not a test bug. This is an Oracle bug. We chose the wrong thing to trust. And the most painful part, the system didn't tell us. The finance reconciliation did. Between AI demos and AI production, between we use GPT and we ship something regulator can audit, what I build sits in that second wall. Production constraints, audit constraints, business risk constraints. A GraphRAG system with a multi-agent test artifact generation in a financial domain. And here is what I learned the hard way. A lot of testing wisdom we rely on doesn't break loudly. It breaks quiet. It keeps giving you green dashboards while reality drifts away. So what's next in this series is practical. How to design evals, oracles, and self-heal mechanisms that don't lie. How to build deterministic worlds where you can, and statistical evaluation where you can't. Because confidence is a product feature. If you can't trust what your tests say, you don't really have a quality, you have vibes. This is the framing model I use constantly. Same model, 3 completely different bars. A demo is 1x. It runs once. It's curated. It's for an audience that wants to be impressed. A POC is 10x. Now you need repeatability. You need convincing, not impressive. But production is a grand X, 10,000x. Different audience, different stakes. Users don't know AI is involved and they don't care. They just want it to work. And the failure modes change at each layer. In a demo, you can hide them. In a POC, you can manually patch them. In production, they become operational incidents and reputational risk. So when I say production AI, I'm not talking about model selection. I'm talking about system design and whether you can measure correctness continuously. And this is what production AI looks like. The model is one component, not the system. At the top, the application and the UX. This is what the user touches. Your end user experience really matters. Then orchestration, routing requests and managing flow. Then the probabilistic core, the most important part, the LLMs, tools, retrievals. But what makes it production is everything around that. The guardrails, validators, fallbacks, audit logs, observability, and the part nobody talks about, continuous evaluation. That eval pipeline is a quiet truth teller. It's how you know whether model updates, retrieval shifts, UI changes, or tool behavior have changed the system. If you're a QE, think about it like this. In deterministic software, your test suite is a thing that tells you if the system is okay. In non-deterministic systems, you need something more like instrumentation plus measurement. If you can't measure it continuously, you don't have production, you have a light demo. All right, now the system. Quick context, the domain is regulated, so I'll keep details abstract, but the architecture is real, the stack is real, the lessons are real. The problem we were solving is familiar. Hundreds of test engineers writing UI automation by hand, every release breaks locators, every change request force rewrites. The test team becomes bottleneck. So the brief was, can we take intent for the likes of user stories, specs, diagrams, Teams call recordings, Zoom recordings, and generate trustworthy tests end-to-end, not toy tests. Tests you can actually run in CI and trust. That word trust is doing a lot of work because generating a script is easy. Yes, generating a script you can believe is correct is a whole game. So what we have built has 6 layers. Each layer exists because something else failed without it. At a high level, this is not a test automation framework. This is a system designed to continuously understand, generate, validate, and evolve testing artifacts in the presence of AI. And the most important shift to recognize here is this. We move from executing predefined tests to continuously constructing test understanding. Let me walk you through how to think about this. At the very top, everything starts with input, and these are not clean, structured inputs like we are used to. These are messy, real-world artifacts like user stories, specs, screenshots, logs, incident data. So instead of assuming clarity, the system is designed to extract and synthesize intent from ambiguity. Next, we persist that understanding in a knowledge layer. This is not just storage, this is memory. A connected representation of how components relate, what APIs are involved, what tests exist, what incidents have occurred. This becomes the system's long-term context. And this is critical because without memory, the system cannot learn. On top of that, we have retrieval and reasoning. Whenever a task comes in, the system doesn't just operate on the current input. It pulls relevant historical and contextual data. And this is where GraphRAG becomes powerful. Because we are not just retrieving similar text, we are retrieving meaningful relationships. Then comes the core of the system, the multi-agent generation. Instead of one large prompt doing everything, we break the problem down into specialized agents. Each agent has a clear responsibility. One enriches the story, one decides scope, one generates scenarios, one writes scripts, one validates. And these agents are orchestrated in a deterministic flow. That balance is important. The intelligence is probabilistic. The orchestration is controlled. Then we move into execution. Tests are not run in shared environments. They are executed in isolated ephemeral environments. Think of Docker or Kubernetes. Every run starts clean. Every run is reproducible. Every failure is inspectable. That's what gives us confidence in the outcomes. And finally, we have the feedback and self-heal. Honestly, I'm not a big fan of self-heal loop, but you need to have that for a few reasons. And failures are analyzed, classified, either corrected or escalated, and that is what's more important. Self-heal with accountability really matters. More importantly, they are fed back into the system. So over the time, the system doesn't just test better, it understands better. Now, if you step back and look at this whole architecture, one thing becomes very clear. Every layer exists because something we used to rely on in traditional testing is no longer reliable. Inputs are no longer clean. Outputs are no longer deterministic. Oracles are no longer absolute. Environments can be shared. And failures can't be treated as one-dimensional. So instead of forcing old patterns to work, we have built a system that embraces that complexity. Now, to really understand how the system holds together, we need to start at the very first layer. Because everything that follows, retrieval, generation, validation, that depends on one thing. The system behaves the intent is actually is. And in this world, intent doesn't come in neat structured format. Let's get into how we ingest and interpret intent in the first place. The layer one is the intent ingestion. And this is where a lot of teams underestimate complexity because the input isn't just a Jira story. It's acceptance criteria, links to epics, comments, its specs and runbooks, its diagrams, sequence flows, architecture, Figma design specs, its screenshots and recordings from real incidents. So the intent is multimodal, and that's very important. And if you throw away those signals, your generator becomes a guessing machine. We treat everything as intent evidence. We embed it, we tag it, we link it. So later layers can reason about what the system should do, not just what one text field says. And this matters for testing because it changes the question. You're not testing, did the output match the prompt? You're testing, did the output reflect the true intent across artifacts? If your intent ingestion is weak, your best model will still confidently test the wrong thing. So what you've just seen is the full machine. But to really understand why this works and where it can go wrong, we need to break it down layer by layer. And we start right at the beginning because if you get the input wrong, everything downstream is wrong. And next, jump into the second layer. Layer two is the knowledge graph. And this is a key part that I really enjoyed working on, which was pretty new when we started as a team. And for me, I've never worked with something like this before. This is a long-term memory that survives model updates, prompt changes, reorgs, and all of it. Why a graph? Because relevance isn't just similarity, it's a relationship. We model artifacts as nodes, story, component, API, test, incident, regulations, and so on and so forth. And edges capture meaning. This story modifies that component. This component calls the API. This incident is linked to that test. So when something changes, a regulation, an API contract, a component split, we don't rely on embeddings to notice. We rely on structure. And from a QA perspective, this becomes powerful because you can ask deterministic questions. Why does this story touch? What incidents cluster around this component? Which tests are supposed to cover this behavior? This crafts context into something you can traverse, audit, and test, and that's why this becomes a backbone. Now, you've heard a lot of acronyms: RAG, GraphRAG, embeddings. Don't worry about this. And this is the idea behind the MK Labs, to start with the production story and then go backwards, and then we learn everything about what you need to go and survive in this AI era as a QE. Now, let's come back to the story. It's very important we should talk about why we moved from RAG to GraphRAG. RAG is nothing but a retrieval augmented generation, and GraphRAG is an advanced concept within that, and this gives you more. So to just put it simple, right? If you go and ask a question in Copilot or ChatGPT, generate a test case for a login, it'll do. But your login screen will be different. You may be having sign-in instead of login, or you may be having different context around it. And how do you make the LLMs give outputs that are really meaningful, having your company context, your organization context baked in? And that is what retrieval augmented generation is all about, right? Now, that plain RAG or a vanilla RAG was naive RAG was not good enough for us. Most teams start with that. Embed documents, do a similarity search, loop into it, feed top K into prompt, and it works at first. But the failure mode is settled. Naive RAG retrieves what sounds similar, not what's structurally relevant. And in the engineering systems, the most important constraints often don't share vocabulary. A regulation doesn't sound like a user story. A production incident doesn't sound like a component design note. So when you rely on semantic similarity alone, you can consistently miss the thing that matters most, not randomly, systematically. GraphRAG changes retrieval from find similar text to follow relationship that encode meaning. That means you can pull context that's deeply related, even if it is semantically distant. This is the difference between a chatbot pattern and a production risk pattern. And this slide is blunt for a reason, right? So RAG is fine for chatbots. If the answer is wrong, you disappoint someone. If the answer is wrong, but confident in a production workflow, you create business risks. And here is the deeper problem. Two things that can be deeply related and not look alike: a user story and the regulation that constrains it, a test and incident it should have caught. So the question becomes, do you want retrieval that's plausible or retrieval that's defensible? Graphs give you defensibility. You can explain why a piece of context was retrieved because it's linked, because it's downstream, because it's impacted, not because it had similar wording. From a testing lens, that's huge because it means the context pipeline becomes testable. Given the story, the graph traversal should include these artifacts and exclude those. Structure is what turns probability into engineering. Now, the next layer is ephemeral execution. Every test run gets a clean room. Think of Docker or Kubernetes namespace run, app container, DB container, test runner, spin up, test, tear down. This is one of those things that sound like infrastructure detail, but it's actually quite primitive because shared environments create fake confidence. Data preconditions drift, tests interfere with each other, flakiness becomes normal. Ephemeral runs gives you isolated state reproducibility and parallelism. Same input, same starting state. And when failures happen, you can preserve the container for forensics. From a testing standpoint, this is how you reduce unknowns, right? If you're already dealing with non-determinism in generation, you don't want non-determinism execution as well. You're asking for trouble. You want deterministic walks around probabilistic scene. Clean rooms aren't luxury in AI native QE, and that's how you keep your signals honest. And the last layer would be failure analysis and self-heal. When a test fails, the worst thing you can do is treat every failure the same, because the remediation path depends on failure class. So we classify first. Is it a script issue? Locator here or flow resolver will take care. Is it a test issue, test data issue? Data refresh or provisioning will be done. Environment issue, service virtualization or environment remediation can be done. Then we rerun. If it heals, great, but that's not the end of the story. If it doesn't heal, escalate. And here is the warning, right? Every successful self-heal is a signal, not a non-event. Because autonomy can hide defects. That is why I warn, or every story I hear from companies, autonomous end-to-end script, I'm like, oh, hold on, right? A healed test might be green, but it might now be asserting a wrong behavior, like a toast story that I just shared. So we log heals, correlate them, and treat them as review-worthy events. Heals are telemetry. They are telling you your systems are drifting even when your dashboards are green. Underneath all of this, two pieces of infrastructure sit underneath everything, and most teams ignore them until something breaks. First is the prompt engine, one place where prompts live, versioned in code, templated, parameterized per agent, shared structure, output parsers, and critically, a single place to A/B test, change across systems. I don't know how many of you do this, but A/B testing of your prompt will be really a critical way, because as we spoke about it, in the AI world, in the LLM world, the same input will give you two different answers when you ask two different things. That's what non-determinism is all about, right? So A/B testing will help you balance it out. Second, the LLM rotor. Agents never call models directly. They go through a wrapper that handles model selection, retries, fallbacks, cost and latency routing. Small models for classification, larger for generation, right? And we didn't use a single model for everything. For content generation, we used Amazon's Nova Pro. We used Bedrock models. It's one of the AWS's native models. And then for code generation, we used Claude. For critiques and self-heals, and we use Claude again. So there's a mix and match of these models, because in production, you don't just want output. You want control behavior, observability, and the ability to answer the audit question, right? Why did the system do and why? A boring infrastructure is what turns AI into something you can operate. So that's the system. Now we get to the part that breaks the playbook: testing. And the reason testing gets hard is not because its AI is mysterious. It's because the assumptions we built testing don't hold anymore. Traditional QE assumes stable behavior, deterministic execution, a simpler tester than a system under test, and clean ground truth assertions. In production AI, those assumptions get attacked from all sides. The system changes silently, retrieval changes gradually, outputs vary, self-heal hide issues. So I'm going to break down into 4 categories. There are more, but these 4 that show up almost everywhere, and each one breaks something we used to take for granted. If you remember nothing else, you can't test production AI like deterministic software with a fancy UI. You need a different mental model and a different measurement system. Here are the 4 categories, right? Lack of ground truth, non-determinism and drift, the tester of the tester problem, autonomy hiding failure. What matters is not just these exist, it's that they combine, they compound, they produce green dashboards while confidence silently decays. And notice what's common across all 4. They're all measurement problems, not how do I generate text, not which model should I use. It's how do I know it's correct? how do I know I stayed correct? How do I know the systems didn't recover in a way what masks the real defects? So as we walk through these, I want you to keep one phrase in mind, right? A passing test is no longer proof of correctness. This statement is uncomfortable, I know, but once you accept it, the rest of the design decisions make sense. Let's go one by one. The lack of ground truth. Yeah. Correct is a harder to pin down. The test the agent just wrote, is it the right test? Can run it against the application, see it passes. But the passing test doesn't mean the testing is done right. The toast story is an example. That test passed, it was wrong. So now you need a way to test the test. A human reviewer is one option. But humans look at 20 tests a day, agree they look reasonable. We don't want a vibe-based checks. That's the ground truth problem, right? In a probabilistic system, you usually don't have a clean oracle. The thing you're using to judge correctness itself is probabilistic. Now, how do you deal with it? There's a whole lot of video coming on this, but just to give you a sneak peek or to cover the point here, is multiple weak oracles combined. Application execution is one signal. Differential testing against historical test is another. Property-based checks. Does this test touch the component the story says it should? Each one is weak alone. Together, they are a signal. Number 2 is non-deterministic and drift. Same prompt, different date, different output. We spoke about it earlier. Most people know this is about LLMs. Setting temperature to 0 reduces it a bit, but it doesn't eliminate it. There are still kernel level non-determinism in some inference stacks. That's the easy part. The harder part is drift. The model provider updates the model. Prompts that worked last week behaves subtly different this week. The vector store gets new documents. Retrieval shifts. The application UI changes. The knowledge graph grows. Relationship you depend on get reweighted by traversal heuristics. Each of this is a complex, silent regression, right? No version bump, no changelog. The system just behaves differently. And unless something is watching, you find it from a customer. So we have a continuous evaluation pipeline. It runs a fixed eval set against every day, track drifts across different multiple dimensions. This isn't CI. It's a separate system that runs as long as the AI system runs. The hardness number 3. The tester of a tester problem. This is interesting because the traditional QE works because the tester is simpler and more trustworthy than the system under test. The test code is simple than app code. Test environment is more controlled than production. Assertions are more deterministic than business workflows. When the tester is an AI system, that flips. Your testing system becomes more complex than what it is testing. Your oracle becomes less trustworthy than a thing that it evaluates. So what we did is a push as much as possible into deterministic territory, make orchestration deterministic, make graph traversal deterministic, make execution environments deterministic, make failure classification deterministic. We let probability live only where it has to live, inside the agents themselves. And the probabilistic parts get tested statistically. Accuracy, recall, precision, these are the GenAI metrics. Like how we have DORA metrics in the DevOps world, and we have different metrics for testing. There are certain metrics in those LLM outputs. And again, as I mentioned, we'll be releasing another video which talks about all of this. But these deterministic walls are on probabilistic seams. That's the design principle. This is the one that bit has hardest. Every time you give a system the ability to recover from a failure, automatically you're trading visibility for resilience. Both are valuable. The trade has to be conscious. Here is the shape of it, right? A test fails, self-heal kicks in. It finds a similar element, the test passes. On the dashboard, that's green. In the logs, that's a heal event. Whether anyone reads the heal log depends on the team. The system might be more brittle now because the heel might have latched onto a wrong thing, but you wouldn't know that from a dashboard. This happened to us on the login flow. A selector changed, self-heal found a sign-in with SSO. Instead of a standard login, a test went green. Standard login was actually broken. The heel hit it. Again, this was not happened to us, but just think of like this as an analogy, right? To make it more simple. If you're coming from a non-automation background, this may be a little bit advanced, so you get a way to think around it. So each heel generates a review item. The thresholds are tighter than people want them to be because a system that heals everything tells you nothing. You want it to heal for obvious reasons. Tuning that boundary is its own discipline. But the deeper point is that autonomy is a quality dimension. Anywhere your AI system is allowed to retry, fall back, route differently, or recover, that's a place where failure can be silently absorbed. Test for absorption, not just for happy path. So, 4 categories of hardness. Each one breaks something we used to take for granted. Lack of ground truth, drift, tester of the tester, autonomy hiding failure, to summarize the 4 that we saw. Now the test pyramid. I know different models came back, the diamond model, the trophy model, but test pyramid has been very much favorite model for testers or in the QE world. Test pyramid we have been using for 20 years assumes 4 things, right? That the tests are deterministic, that behavior is stable, the tester is simpler and more trustworthy than the system, and that is a clean oracle. Each of those assumptions maps to one of the 4 hardness categories that we just discussed. None of them holds true for AI system. So what replaces it? I don't know if you want to call it the MK Labs way. I would say a 4 concentric rings instead of 3 layers, a deterministic core orchestration graph ephemeral environment tested with normal unit test around that, a statistical eval ring, accuracy, metrics like accuracy, precision, F1 recall over a fixed eval set. Around that, a differential and a property-based testing, comparing versions, asserting invariance, and surrounding the whole thing with drift monitoring. Always on watching for P95, latency, cost, quality scores in production. This isn't about more tests, it's about better truth signals. Concentric instead of stacked. Continuous instead of one shot. Multi-oracle instead of single source of truth. None of these rings is sufficient alone. They cover the system together, to be honest. Now, I hope this sums up the experience of the test generator that I built, where it failed, the lessons learned. Now, if you enjoyed this, stay tuned because I'm taking a different approach unlike the other channels that you might see. I want to show you what I did in production, and I didn't build that production system overnight. I had a learning journey, I had a path, I had a roadmap, and this is like a bottom-up approach as I mentioned. So this is the production system you saw. Now, everything else in this series will follow all the things that we discussed. Now, if you go all the way back, so imagine you'll be having, say, 12 videos or 15 videos in this series, then end of the last video, you will understand everything from basics. And you can again, come back and rewind on this very first video. That will be great. This was the opener, the landscape. The series gets practical from here on, as I mentioned, from a bottom-up approach. You have seen what is possible, how it was implemented. Now we will see from ground up how to build such a system, right? So next up, we'll be discussing the 3 anti-patterns I see almost in every testing engagement. Patterns that look reasonable until you realize they manufacture confidence. Then eval pipelines that catch drift. Not toy evals, always on version, big enough to mean something. Stay tuned, subscribe, and share this to your network. See you soon in the next video. Until then, take care.